Hello and welcome to this video. What I want to do in this video is introduce field programmable gate arrays to some extent, but specifically to introduce the DE10-Lite board and how one could possibly program this using the Quartus Prime. Now, the DE10-Lite board is a board made by Terasic, but the chip on it, the FPGA particularly that is on this board, is made by Intel. So is the Quartus Prime software made by Intel. But while I want to talk about that, let's start from somewhere relatively weird that might seem a little weird. Say we had this grid on the screen. I wanted to display a pattern on this grid. We could consider the entire grid and say, okay, how many squares are there on the grid, and determines what happens in each grid all at once. But instead, we could just take one box within this grid at a time, just one cell at a time, and we could ask the question, what should be inside this cell? Now, it makes sense that, say, for example, I wanted to write the letter T. I could decide to fill this in with red, and this down here, and suddenly I have the letter T just by filling some specific cells. Now, to have filled this cell, I would have checked, say this is the first cell here, I could have checked this first cell and asked what color should be in this cell. Say I say red, this next cell, red, next cell, red, next cell, red, next cell, red. This cell, nothing, black. Next cell, black, next cell, black, next cell, black. I could go all that way, come back to the next row, and keep asking the question. I get here red, and then keep asking the question all the way until I've gone through this entire grid. That way, I have been able to determine what should be inside every particular cell on this grid. Okay, so that is one way we could go. Now, it's probably obvious from the example I just gave right now that for each cell, I'm simply asking a yes or no question. Should it be red or should it not be red? That's all the question that we asked so far in this case. Should it be red? Should it not be red? Should it be red? Should it not be red? Now, let's make things a little more complex. Okay, so we can make things a little more complex by making the question a little more, okay, let's make this black, so I just take out this red here. Now, we could make the question a little more complex, where we are not just asking, should it be red or not red? Rather, we could ask the question, what should be the color in, or we could ask the question, what shade of red should be in here? So if there are 8 different shades of red, then if we're going to represent that number with binary numbers, we could use 3 binary numbers. In other words, each binary number has 2 possible states. If all we're interested in was red or not red, we could just use one binary number. That binary number, if it is 1, then we say it is red. If it is 0, we say it is not red. On the other hand, if we wanted to have 8 different shades of red, we would need 3 binary numbers, and the combination of the binary digits that we have will determine what shade of red it is. So, for example, if we had 000, we could say that's pure black. Then 001 could possibly be a very dark shade of red. 010 could be a lighter shade of red, all the way until we get to 111, which would be the bright red. So that could be for several shades, for 8 shades of red. What if we went one step further and we said we want to have 256 different shades of red? Okay, 256 different shades of red means we need 8 bits, 8 binary digits to be able to define that. What if we wanted to do more than just saying red? Let's say we wanted to have any possible color like we see over here. We wanted to pick any possible color. Say we picked yellow. Okay, I could put yellow, yellow, yellow. Okay, so let me not use yellow. Let me use a different color because I would find it difficult to take off the yellow without in this trying to grid. So let's say we had cyan, this color, this shade of blue in here. Now, this is not pure. It's not a dark blue. It's a rather light blue. It's somewhere between blue and white, if you want. And how do we get this particular shade of blue? Well, we could have a different. We could say that each of these boxes here, each of these cells will be filled with a specific combination of red, green, and blue. It just turns out that if we use red, green, and blue as our primary colors, we end up with any possible color out there. And you probably have seen this before. If you haven't, it's not a problem. But if you go to, for example, a color palette in any image editing program, typically you would have a way to select any possible color. So I could move this around and change this color to whatever it is I want. Now, originally it was somewhere around cyan, Okay, that's not exactly the shade. I think it was probably this shade, but okay, let's just cancel this. I think it initially showed us the exact shade we were at. So this was the original shade we were at. How do we arrive at that? Red was 153. Red was at shade 153. Green was at shade 217. And blue at shade 234. Using that particular combination, remember we have 256 different shades of red, 256 different shades of green, 256 different shades of blue. Then we can specify this particular shade of blue. If we move this, say for instance, to pink, now our red could be 240, green 147, blue 238. We could decide to make this darker or make this brighter. Again, notice how all these shades are changing. If we just went to pure white, each one of this is 255, 255, 255. If we went to pure black, each one of them, okay, so if I could make this black, proper black, 0, 0, 0. Each one of them is 0, 0, 0. So 0 to 255 gives me 256 different possibilities. So we've said 8 bits to represent red, 8 bits to represent green, 8 bits to represent blue. That gives us a 24-bit system, and that is why you often talk about 24-bit color. But however, this is really not the focus of what we're doing today. So if you haven't understood much of what was said today, kind of ignore it, because that's not the focus really of this video. However, what we have shown is that something quite complex, as showing an image on a screen, okay, showing an image on the screen, you could accomplish that quite easily by dividing up your screen into several cells and deciding just what happens in each one of those cells. To push further this example on images, this is actually how every screen works. You talk about pixels in screens, and each pixel on the screen is a cell on the screen, and all your video rendering program does is to determine what should each one of these pixels be, what color should each one of these pixels be. If you have a pure black screen, then each one of those pixels has 0, 0, 0 as the shade that you have in there. So all you do is determine the shades of each one of these. So I hope that at this point, I've somehow convinced you that a screen, every single screen out there, can be controlled by a digital system. Now, that's the point I just want to raise, that we could have digital systems controlling so many things, and we do have digital systems controlling many things out there. Some things that we might not necessarily take note of, except that nowadays most things are powered by microcontrollers. But I specifically picked up this example and talked about digital systems in this way to show that each one of them really, each of this the example I just picked really is just all about pure logic. Is it on? Is it off? Or what particular digital value can we use to represent the red, the green, and the blue for this particular pixel? You could extrapolate this and use and talk about a neural network system. What should be the weight, or what should be the weight? What should be the bias for a particular neuron out there? The input or the output of the particular neuron, what should be out there? And it's possible to hard code a number of these values in there as digital numbers. So it stands to logic that if we have just an array of logic gates, we can possibly do a whole lot of things with just an array of logic gates. It's possible to do a lot of things with just an array of logic gates. So now I come to the field programmable gate array. A lot of smart people out there, this particular FPGA is made by Intel Corporation. I'll leave this, okay, so I'll probably just make this link available to you in the description. This particular field programmable gate array is called a Max10, is in the Max10 family. And here, what you have in here is that you have up to 50,000 logic elements. Now, they just call logic elements, not so much logic gates. We won't go into the details of why they are called logic elements, but think of this as just simply AND gates, OR gates, NOR gates, NOT gates. Well, NOT gates, NAND gates, and NOR gates. Just think of each logic element as that. It's a little more nuanced than that, but for now, let's just keep it that simple. Actually, what you often have are multiplexers, but again, keep it as simple as logic elements. Up to 50,000 logic elements in there. That's showed by the white space. I mean, you're not going to draw each one of those 50,000 elements within this space. This packaging, by the way, is as small as 3 millimeters by 3 millimeters. Within there, they're able to pack up to 50,000 logic elements. A number of DSP, digital signal processing blocks, which are specialized logic elements that are good for signal processing, specifically for signal processing. You have some RAM in there, often called block RAM, because there are blocks of RAM in there. So often called block RAM. You have DDR controllers. DDR stands for RAM and random access. Well, DDR. DDR3. I'll leave that. I don't want to try to remember the full meaning of that right now. But you have the DDR3 controller controlling the RAM. You have a 32-bit processor which runs the NIOS 2 system that you have on this particular chip. You have an on-chip oscillator, an on-chip clock, a number of input-output banks. That's this cyan colors or light blue colors, or is powder blue now. Well, whatever shade of blue this is. You have 8 of them all around the FPGA, and then you have some phase lock loop elements also on these 4 to be precise. You have a power regulator. You have some analog to digital converters, and you also have flash memory, all within this 3mm by 3mm chip. So an FPGA is an IC that is made up of several logic elements. Usually there will also be DSP blocks, some memory blocks, and some power regulation. In some other cases, you will also have an on-chip oscillator. Most of them will also have an on-chip oscillator, in which case an on-chip clock and some PLLs in there. Most of them will have that. Not all of them will necessarily have a processor. I could say that this processor is not so much, it is not an SoC board, a system on chip board, in which case this processor is more of a simulated processor that is made using logic elements, but that is for another video. So an FPGA looks something of this nature. Odds are that if you're going to work with an FPGA for the first time, you will not be buying the Max 10 chip on its own. Rather, you'll buy the Max 10 chip with some support structure in quotes. So here I'll go to the Terasic website and show a board that was made by Terasic, the Terasic company. This is the DE10-Lite board, and on it you have a Max 10 FPGA device. So Max 10 is a family of devices. The specific make of this particular Max 10 is 10M50DAF484C7G. What does all those stand for? Well, each one of these numbers means something. We'll not go into all of that right now. Really, it's not that important. That is not for this video. But then the FPGA on this is a Max 10 FPGA. Then it also talks about the various things that it has in there. Some of these we've already seen on Intel's slide. It's the reason why I bring this particular one up is that this shows you what the board. So the FPGA is at the very center of the board. But beyond the FPGA, on the DE10-Lite board, you have a couple of other things. Now we know that the Max 10 FPGA had 8 input-output pins, 8 input-output banks rather, 8 input-output banks. Now to be able to work with that, you have GPIO ports, you have Arduino headers also that are connected to the Max 10 FPGA. So these are all wired up. So the FPGA itself is an IC on this board, and then you have a lot of wiring that comes to various peripherals that you have in there. So you have a number of resistors that are connected to a VGA output, so that you can connect a VGA display to this output. Now notice this is 4 bits, not 8 bits as I used in my present example. You have a number of push buttons that can serve as inputs to the FPGA. They have been debounced already. That is for another video. You have a number of outputs here that are LEDs. You have slide switches, 7-segment displays, an Arduino header. You have an SDRAM also on the board itself, apart from what you had on the FPGA itself. You have a USB blaster that is used for programming the FPGA, the Arduino header, and then a GPIO ports, GPIO connector pins. You also have an external clock to the FPGA. So what this board does is that it gives you a number of peripherals that makes it quite easy to interact with the Max 10 FPGA. I mentioned this because the DE10-Lite board is the board I'm going to use for this video, and it's good for it's a good entry-level board. You could get this on the Terasic website. It's a very good entry-level board. If you get this board, my recommendation, so it costs $140, but for academic use, it costs $82. If you get this board, I'll recommend coming to this page and going to the resources tab. On the resources tab, you see a number of you see the user manual. Then you also see the DE10-Lite CD-ROM. With the DE10-Lite CD-ROM, you have a number of, well, it just makes it a good starting point. So let me just keep it at that. And the manual could also be quite good. There are things that are called daughter cards. To try to illustrate that a bit, I'll go back to the specifications page. if this doesn't take too long. So there are a number of peripherals you can connect to the board itself, okay? So if I scroll down here, okay, so for example, you have a touchscreen connector that you just plug into the GPIO connector on the board. This is what the board looks like, by the way. You connect a touchscreen device onto it, multi-touch device onto this. You can connect the cameras onto it. You can connect several, there are a number of boards that you can connect onto this. Not very many of them, but you can connect a number of boards to it to just, again, for a number of projects. Okay, so let's go ahead and work with the board. Okay, so firstly, what I'll just do is show you, this is the board which I'll be using again. This is a DE10-Lite board, like you just saw on that particular slide. This is the DE10-Lite board that I'll be working with for this video. Now, to program a DE, so particularly for this video, I'll work with the, there are a number of laboratory exercises that come on Intel's website. These are specific for the DE10, for the Max 10 FPGA, but they are targeted at the DE10-Lite board itself. So you'll see DE10-Lite board or the DE0CV, excuse me, or the DE1 SoC board. So these are the three boards that they target with this particular set of laboratory exercises. They work well with on the DE1 SoC board, you have a different type of FPGA on it, but really these exercises can be performed on any of these boards and they work perfectly fine. Okay, so we're going to run through this part one of this laboratory exercise one, and I'll just simply run through that in this video for the remainder of this video, and that'll be it for this video. So we've mentioned that we have an FPGA. It's simply an array of gates, okay, an array of logic elements interconnected in special ways. Now, how do we make this particular FPGA do a particular function? Well, we need to tell it how to do that, and we do that through a hardware description language. Now, it is called a hardware description language because really what you are doing is describing what the actual hardware should be. So, for example, you could say, I want to connect an AND gate to an OR gate. I want to connect it in this specific way. I want to connect this clock to so and so place. I want to connect this and this and this in this way. So it's a description of what the hardware actually looks like. Bear in mind that when you are done with your design, what you have done is to describe how a hardware will be implemented and what the software will do, what the compiler will do, the compiler for that particular HDL, hardware description language, what the compiler will do is to interpret what you have said and compile it. I shouldn't use the word interpret because it's not an interpreter. To compile your instructions into a hardware specification and a hardware netlist and actually burn that onto the FPGA. Better still, we'll actually implement that on the FPGA. So what will now happen in here will be that you now have an electric circuit. A logic circuit is what will now be interconnected in here. I run through all these explanations because when we now start running through the actual programming, there are a number of steps we need to go through. So I've mentioned that we're going to have to create a hardware specification, which will be done in an HDL, in a hardware description language. So think of that as your computer program that you're going to write. But then don't think of it just as a computer program because it ends up programming, creating a circuit on the FPGA. Now, if this FPGA had several logic elements on their inside, and I want to connect, say, where are the switches? Okay, sorry, the switches will not show up here. So let's say we have these slide switches. I want to connect the slide switches to the input of to some of the inputs of the FPGA, and I want to connect some of the outputs of the FPGA to this LED. How do I make that happen? We have to have a way of specifying that, okay, FPGA, I know you have 50,000 logic elements. These are the specific logic elements I want you to use. Don't use the whole 50,000 of them. You need to use only 20 logic elements for this particular project. So use this particular 20 logic elements. Then I want you to connect to this particular input. I want you to connect to this particular output. Okay, so you can do all of that within, you have to have ways of specifying all of that so that the circuit is actually connected the way you want, and the slide switches will actually serve as inputs and your LEDs will serve as outputs. I use that example specifically because this first laboratory part one talks about simply connecting the switches to the input of the FPGA and wiring them directly to the outputs of the FPGA. So we're not doing any logic function. All really we're doing is just wiring them from inputs to outputs. Now, there are two popular languages that are used as hardware description languages for defining logic circuits. One is Verilog, the other is VHDL. This code here is written in Verilog. Okay, this particular code here is written in Verilog. It can also be written in VHDL. They tend to be quite, those are the two popular languages that I know of. There are other languages like System Verilog, AHDL, but the most popular ones out there are VHDL and Verilog. For this video, I'll make use of Verilog, largely because this was requested by someone. I really will not be writing the code, nor will I be explaining the details of how Verilog works. However, I'll just simply copy this code as you have it in here, and I'll simply use this code because this for this part one, there really is not much. It's to get used to the environment and get used to how to write your programs. Suffice it to say, however, that this Verilog code tells us that we're creating a module. In VHDL, they are called entities, but in Verilog, they are called modules. We are creating a module that has input. Let's say has an input. I'm concerned about using that word "and," but I'll explain in a bit. Has one input whose name is SW, but that input has 10 bits. So it's a 10-bit input. So if you want, you could think of this as 10 separate inputs. One called SW0, SW1, SW2, like that. But then, say it has one input, one 10-bit input, and one 10-bit output. This is we usually number the ports from the most significant bit to the least significant bit, both in VHDL and in Verilog, because it's easy. When I say 001, for example, typically we think in decimal, that is 1, because we usually call the most significant bit first and least significant bit last. So when writing our code, we like to write most significant bit first and least significant bit last. So we start from 9 down to 0. Okay, so we have a 10-bit input and a 10-bit output. Then we now come over here where we tell Verilog we tell the compiler how to implement the circuit. In this particular circuit, we are simply saying wire the inputs directly to the output. So assign the output to the output, assign SW. So SW just simply is wired directly to the input. Let's say I had said SW and so, then you will have an AND gate between SW and something, and that's what will get connected to the outputs. So let's go ahead and implement this. To do that, I need to bring up Quartus Prime. So this is Quartus Prime, the Lite edition. It's free. So we'll just go ahead and use this. I'll click on New Project Wizard to create a brand new project. We're going to give it a project name. I'll just change the location of this. I like to place my FPGA projects inside the same location. FPGA projects, there you are. I'll create a new folder for this, call this online. Okay, so that's just a folder I want to keep various projects I work on in here. Then I'm going to create a project. Let's call this Lab 1. Lab 1-1, since it's actually part 1 of this project. So I'll say, okay, sorry, that does not exist. I want to create a folder. Okay, no, that's good. I'll just select this folder as is. Asking me what's see FPGA projects online, places wherever it is you want. What do I want the name of this project to be? Lab 1-1. Or if you want _1, just your choice. Top level entity, what do I want it to be? If you want the top level module, what do I want it to be? I'll keep it as lab 1_ or lab 1-1. Next, I'll make this an empty project because I don't have any of the source codes yet. If you have codes that you want to add to this directly, just go ahead and add them here. But I don't have any, so I'll just simply do next at this point. Then this is quite important. This here we need to specify what device we are targeting. We need to specify what device we are targeting. Now, if we come back to what we have over here, this tells us the particular device we are targeting, which is 10M50DAF484C7G. Now, if you remember all of that, we could just come in here. First of all, we need to specify this is max 10. We could come in here and just simply type all of that. 10M50DAF484C7G, I believe is the name. This is the device over here. And we could click on next. Another way we could have gone is to go to, over here you have device or you have board. If we select board, then you could come over here and look for DE10-Lite. If you have DE10-Lite, then go ahead and select it. If you don't have it, then you might have to come to check the design store. So you could click on this and now oh, sorry, this is Cyclone 5. Let's say Max 10. So go to Max 10 and we're looking for the DE10-Lite. So this is DE10-Lite board. Okay, so this is the DE10-Lite board. So you could select that. However, I don't always do this. Reason is that if you come and look at the device specific that is specified over here, this device is a 10M50DAF484C6GES. What we have is the C7G. So I will not select this one. Let's see. I want to see if any one of them actually corresponds to this particular. So none corresponds to this particular board. So we could go to the design store and try to download more recent boards from the design store. But since I know the name, I'll just go ahead and use what we have over here. Next. For simulation, I have Questa Intel FPGA installed, but I'll just simply keep none because I really am not going to do any simulation over here. And I'll go next. This gives me a summary of everything I've selected, and I'll go ahead and finish. Open from trusted sources. Yeah, go ahead. Open from trusted sources. Now I have a project created. It's doing some work behind the scenes. I've created a project. I can't go ahead and write I can go ahead and write my code right now. So I'll go ahead and create a new file. So new. When I do that, it brings up this and it asks me what type of design file do I want to create here. So this gives you different ways we can design my hardware. I could use VHDL, I could use Verilog, I could use AHDL, System Verilog. For this case, we're using Verilog. So I'll say, okay. I'll just come here and paste the code I copied from the Intel lab. So this is what we have over here. Save. Okay, so it asks me what file name I want to save it as. Okay, so save, Control S. Now it's asking me what name I want to save it as. It's a good idea to save it by the name of the top level entity. So lab1-1 save. One more thing I should do here. This name is not what we said our top level entity will be. We said top level entity is lab1-1. Okay, so so this is a problem. Now this is the reason why I should not have used a hyphen in my design name, because Verilog does not like this. I could go ahead and compile this file to just show you what I mean. So I'll go ahead and do analysis and synthesis. Go ahead and just compile this file. And okay, sorry, two more things I need to do actually. Firstly, so I'll just let this go ahead and compile. But I expect it to throw an error. And the reason is that I created a new file, but I haven't quite added this file to my project. So, okay, it doesn't, okay, so it went ahead to add it to the project, but it did not like this hyphen in there. So this will not work for us. I'll close this up, close this project, and create a new project entirely. So let's just go ahead and create a new project wizard. Yes, go ahead, just close this down. So one, if you want lesson you have over here, never use hyphen. Always, if you have to use a special character, use underscore. Okay, so I'm going to use underscore for this particular case. Already contains the project, so no, I don't want to do this. Sorry, back. So I want to create a new folder. So I put this inside a subfolder in the lab1_1. Okay, so select this folder. Select this folder. I'll go ahead and use that in there. So I'll just run through this very, very quickly because we have already done this. 10M50DAF 484C7G, I believe it is. Next. Now, if you select the wrong device, okay, if we select the wrong device, we will end up with a problem where it will probably compile, but it will not be able to implement the circuit on the device because it does not understand the device, the specific device that we selected. So here we have our projects. Just go ahead and create a new HDL file once again. Paste my code in there. Save. Go ahead and save. And now I can go ahead and compile this. Now I could click on compile design, but instead I'm just doing analysis and synthesis. The reason is that I want to make sure that there are no errors in this. If there are no errors in this, then I'll go ahead and show what the others, well, I won't go into much details of how the others work. However, I'll talk about at least what they work and why you have to have several things in here. While this compiling, let me go ahead and talk about that. Now you have the filter. Okay, so top level design into my apologies. I forgot to change this name. lab1_1. So it's saying it could not find lab1_1, that particular device called lab1_1. So let's go ahead and compile this once again. Now, once we compile this, it tells me that the syntax is okay. Okay, it could tell us that the syntax is okay, but it doesn't necessarily tell us that everything is fine. It doesn't tell us it can be implemented on the particular FPGA we selected. It does not actually implement it on the particular FPGA we selected, but then it tells us that the syntax at least is fine. Now, if we want to implement it on the device, so here the syntax is fine. By the way, you could see what a summary of this. We're expecting to use the total number of pins we expect to use is 20 pins. How many logic elements are we using? 0. Why? We're just simply connecting input to output. So it makes sense. We are not using any logic elements, no registers, no memories, no virtual pins, no multipliers, no phase lock loops. Nothing else is being used. We're just simply using the inputs and the outputs. That makes sense. Now, it has a circuit. It has a definition that works. But we now need to fit this particular design we have to the FPGA that we have. That's where you now have the fitter, which is place and route. Okay, so if we run place and route, you have to have run analysis and synthesis before you can run place and route. Now, if we run place and route, it will do its best to now try to find a way to route to implement our circuits on the FPGA. Okay, so it finds a way to try to implement our circuit on the FPGA. So now it has found a way to do this. We could tell it, okay, assembler, to go ahead and actually generate program files that we're going to use to actually program onto the board, and then timing analysis. By the way, maybe I should actually pull up let me show what my let me see if I can pull up a video of the FPGA. Okay, so the board is up, so you can see that nothing has happened on the board just as yet. Then we have the netlist writer, so it just runs through all of this. Now, do we have to click on this one at a time? No, we could have just clicked on compile design, and it could have gone ahead to just run through all of these steps. So once it's done with all of this, then I can click on program the device. That pulls up this environment, and if we see the device in here, then we can go ahead and click on start. If you don't see the device in here, go to hardware setup. That pulls up this menu. Go to hardware setup and make sure you have USB blaster over here. If you don't, double click on it in here, and then we'll add the device in there, and then you should be fine. If not, you want to check your USB blaster setup. So since this device is in here, I'll go ahead and program. Now I'm going to resize the video a bit so you see how the board responds once I program. Once I click on this, then you see a light that shows it is programming. And once this is done, we see 100% successful over here. Now the board is ready to respond to me. So I'm going to flip the switches. I'll use one hand to hold and then flip a switch. As I flip each switch, okay, now as I flip the switches, I hope you can see nothing is happening. I'm going to flip all the switches. I flipped all the switches, nothing is happening. Okay, I flipped all the switches, nothing seems to be happening in there. Why is that? Now, the reason is that we left one thing out. And remember, we said we have created a hardware specification. We have checked it, and the code is good. And we have told it to find a way to implement it on this particular definition of device. Now, where specifically did it place it? What input did it connect to what output? In our code, we said the input is called SW. We said the output is called LEDR. Okay, so what particular device should it connect to the input? What particular physical device on this board should it connect to the input? What particular physical device should be connected to the output? We have not specified that. And that is what we need to specify. So there are a number of ways to do that. And one way is to come to assignment and go to the assignment editor. If you pull up the assignment editor, notice there is no assignment as at this point. We have not told it how to assign anything. And we can go here and one by one assign each one of the inputs. Now, I said each one of the inputs because you have SW0, SW1, SW2, SW3, all the way to SW9. And then you have LED0, LED1, LED2, all the way to LED9. All of those have to be assigned. When you have assigned all of them, then we're going to run this compilation process all over again because now we have specified the input and the output. So I've run through all this procedure to show that writing your code is one thing, implementing it on the actual FPGA is also quite important. So I could do that through the assignment editor, but there is another way to go, and that's the method I want to show at this point. This came with the system CD. Remember I said you can get the system CD from the Terasic website. I say if you go to resources, you'll see the system CD, and on that site you can get the system CD. On the system CD, you have this particular tool, and this tool can be used for generating the assignment generation. So here, I can select specific things. I can say, okay, I want to use the clock. I want to use 7-segment display. It highlights this, by the way, whenever I click on each one of these, on any of these. But in this particular case, I'm just interested in the 10 switches and the 10 LEDs. Now I go ahead and I tell it generate. Okay, it asks me, where do I want to save this? Where do I want to save this particular file? So remember, we have things saved inside FPGA projects. Then we have online. So I'm just going to place it inside the same folder. Then we have lab1_1. That's the name of the folder. Then I will put this under, and I'll create a folder called System Builder. I'll just create a builder. That's the name of this program, by the way. I'll create a folder called System Builder, and then call this, say, lab1_1. And I'll say save. Now, the reason it's saying this part does not exist, okay, try again. So I can go ahead and create, let me go ahead and just create this. Sorry, just give me one moment. So open this folder first of all, and then I want to create the folder called System Builder. Okay, so I create a program, the folder called System Builder. The reason why I'm creating that, I'll just leave this, oh no, let me call it lab1_1. Okay, one more thing I should have done. Let me come back. Let me copy this name that I've just created here and cancel. Here it asks for the project name. I should have changed this project name to our project name, which is lab1_1. Click on generate. It asks me where I want to place it. Yes, go ahead and create it here. I created a subfolder and I'm placing it in the subfolder. It's telling me project successfully created. The reason why I did that is that I want to make sure that I don't overwrite what I did already. Okay, so when I use System Builder actually creates a brand new project. It creates a brand new project, so you could start from there. It's actually a good idea to start from there, particularly when you're just learning, just that I never start from there. So if we go into System Builder, sorry, hold on. You said you were successful just now. Let's do that just one more time, sorry. So it generates, I want to make sure I'm inside the correct folder. Nope, it's not in the correct folder. So let's do that again. Sorry. C FPGA projects online online lab1_1. Now inside this System Builder, yes, go ahead and save in here. So it is saved into this place, okay. And let's check the System Builder folder. So now we see the files have been created in here. You also have this an HTML file that also been placed in there so you can read on how to use this. Now, I'm actually interested in just one thing here, which is the QSF file. It's a specification file. That's all I'm interested in. But I could go ahead and open this project to see what it has created. It created this using Verilog, so it just gives you a starting point you can start from. But I am actually interested in this QSF file. I'll open this QSF file with a text editor. And this is what the QSF file looks. It is a global assignment. This effectively is an assignment editor. Okay, so here we're able to assign things. And it gives the default name LEDR. Now, if we are not using LEDR, let's say we're using a different name to represent our outputs, I'll change that name over here. But we used LEDR, so I'll just keep it as LEDR. Then we selected the switches as well. So it tells us how we are selecting the switches. It tells us that the technology is 3.3 volts low voltage TTL. And then it tells us the particular pin to connect each of these switches to. In most cases, without these particular lines, it will still work. However, it's good practice to specify what the technology one is using is. Okay, so this tells us which particular pin of the FPGA to connect to what. Remember, it's a hardware. The FPGA itself is an IC. So which of the pins of the IC are we connecting to the switch on the board? Which of the ICs are we connected to the second bit of the switch, to the second switch on the board? which pin are we connected to the third switch on the board. Remember, these are physical. We're telling you which physical device to connect to which physical device, and at the same time, which LED to connect to which particular physical pin. So with this all specified in here, I'll go ahead and copy this QSF file. Remember, I said that's all I'm really interested in. I'll go into my actual project folder, which is this, and I'm going to overwrite this QSF file. If I open this QSF file before overwriting it, just to show what is in here, notice you don't have any of those specifications for the LEDs or for the switches. All you have in here is stuff telling us what the particular device we're specifying, we're targeting is, and when this was created and all of that. So really, I could say, okay, let me not overwrite this. Let me just copy what I need from in here and paste in there. And so I could come and I just say, these are comments, by the way, so I could just take it from here. It really doesn't matter. But I'll go ahead and just take it from here because I like to have those comments in there. It just makes it look a little better somehow. So I'll paste it at the bottom of this, save. Go ahead, minimize this. I'll minimize this as well. Now I'll come to my assignment editor. Remember, we still haven't defined anything in here. All we did was change that QSF file. Now by doing that, if I come to my assignment editor, notice it has populated all of this, and that is a whole lot faster than having to type this one by one, okay? So it's a whole lot faster than typing all of this one by one. I can just go to a text editor and edit all of that. Now, because I have changed my assignment, I have to compile the entire thing all over again. So now I just clicked on compile design. It's going to run through this entire process: analysis and synthesis, the filter, assembly, timing analysis, EDA netlist writer if necessary, and then we will be able to go ahead and program this device once again. So this will take a few minutes or a minute or two thereabout. So if it takes a little while, I may just pause, I may just speed up the video and cut to the point where it is done compiling the entire device, compiling the entire design, compiling the entire project, I should say. I haven't said much about timing analysis, largely because, well, that's outside the scope of this video, but timing analysis is something we often do a lot of. Okay, so I'll go ahead and program this device. The EDA netlist writer is actually not needed because we are not using any EDA tool for this project. So I'll go ahead and, okay, so it just occurred to me that, okay, it's good. I've had the image on all along. Okay, just testing that the image is live. So I'll go ahead and program this. And this time now you see things are a lot different. Two things to note. One, the LEDs are all very bright. Previously, they were in the unassigned state, so they were slightly dim, neither fully bright nor off. Now we see some of them are on, some of them are off. And okay, so I'll lift this up just a little bit. So if I can put it in front of the camera. So you see some of them are on, some of them are off. Some of the switches are flipped, some are not flipped. I'm going to flip one or two, and you will see the LED respond to it. Okay, so switch that off. Switching the second one off, switching the third one off. So now the LEDs are responding because they are now connected. Okay, so bear in mind, you create your design, but you also have to specify how these are supposed to be physically connected. Okay, you still have to specify how these are to be physically connected together. When you have specified how they are physically connected together, then they can actually be connected together. The board has several peripherals. For instance, there are some push buttons over here. If I press the push buttons, nothing happens because there's no connection to them. There's no functionality that says how that should work. Okay, so that will be it for this video. I do apologize. It has been longer than I thought it will be, but that's it for this video. See you in the next one.